How's it going? Hope y'all are doing alright. Alright, did y'all have any questions on the homework, first of all? For the intercepts, August, as long as you're writing them as ordered pairs, that doesn't really matter if you write them separately or together, because we can just tell from the coordinate whether this is an x-intercept or a y-intercept. It's like 25, as long as you write down negative 2 comma 0, 0 comma 3, and 2 comma 0 as the intercepts, and that's perfectly acceptable. Yes, sir. Alright. Just let me know when you're ready with it. Let's see, 27, and you can see that right here. Zoom in. Okay. Okay, the intercepts, clearly this is 0, 1 is the intercept. For domain would be negative infinity to infinity. Range would be from 0 to infinity, vertically. And it is increasing from negative infinity to infinity. I'm not sure what your question is, though, August. We can see the function's increasing this whole time. Starting from the far left, there's a upward slope the entire time in the graph. That answer, 0 to infinity, is actually the range on part B. is vertically, it doesn't drop below y equals 0, and it goes everything above that up to infinity. That's okay. But it is increasing negative infinity to infinity. Yeah. Were there other questions on homework? Mm-hmm. Okay. Today we'll be wrapping up. We'll do the other half of section 3, and then we'll also look at section 3.4 today. On Wednesday we'll look at section 3.5, and then I'll get the review ready for you because our test will cover 3.1 through 3.5. So on Wednesday I'll make sure I upload the review, and then on Monday next week we can go over any questions on that, and then our test will be it'll be scheduled for Wednesday next week, but again I'll probably give you from Monday night to the following Tuesday or something like that, or well, Monday night to Sunday night, not Tuesday to Sunday night. So anyway, yeah, so see, this Wednesday is the 7th, so our next test will be the 14th. Okay. So last time in section 3.3, we talked about increasing, decreasing, and when a function is constant. So this time we'll talk about what we call local and absolute extrema. Let's start off with absolute extrema. So when we say extrema, we are referring to the extreme values of the function. And so what that means in this context is the absolute extrema, there's only two values we're looking for, the absolute maximum and the absolute minimum. And what the absolute maximum and minimum are the two single, each one is the single highest and the single lowest point on the graph. Okay. So the absolute maximum is the single point that's higher on the graph than all others, and the absolute minimum is the lowest point on the graph lower than all others. So let's look at some examples, just graphically. This has a very graphical aspect. Okay, so we look at this this curve. Here we can say we have an absolute minimum, because that is the single lowest point on the graph vertically. This stops at a single point, and that's the lowest point on the graph. This one, because we have an arrow, and the arrow, of course, indicates it keeps going, keeps going to the right and keeps going up to infinity. Because we have the arrow here, we would say there's no absolute maximum. Because there's no one point that we can say is higher than all others in that graph, because as soon as we pick a highest point, there's going to be one further than that, because the arrow just keeps going on and on and on. So in this particular graph, we have a minimum, but no maximum. For this graph, we see the graph stops here, and over here it does have an arrow saying it continues downward. So the graph stops here, but this part is actually higher. So there's going to be a point on this curve where we do have an absolute maximum. But because the arrow means it keeps going, we would say there's no absolute minimum in this case. Even though visually it's a little bit deceiving, but because we have the arrow there that says it keeps going, it does continue on and on and on towards negative infinity in this case. So we need to be careful that when we look at the graph, from a visual standpoint, we still have to understand what the arrows mean and how does that specifically impact the presence or lack of absolute extrema. And that's really what's going to prevent it from happening in a lot of cases. If the graph has an arrow on it, which means it just keeps going, and there's no absolute value in that case, no extreme value in that case. Anyway, so that's absolute minimum and absolute maximum. And that together, that's what we call absolute extrema. In the kind of a similar vein, we have what's called a local maximum and a local minimum. So let's look at our local extrema next. Oops. Sorry about that. So we have a local maximum. Now when we talk about local extrema, these are points that in a certain vicinity or in a certain area of the graph, these are the single highest or lowest points. But they may not be the absolute extrema. Only in a small area of the graph are they the biggest value. The easiest way to distinguish a local maximum is this is a point where the graph switches from increasing to decreasing. Okay? Because what happens is right here, at the top of this hill, we know that this has an arrow, so the graph is just going to keep going both directions, but right here it switches from increasing to decreasing, so this is a local maximum. And in fact, if we only looked at part of the graph, that would be the single highest point on that graph. Okay? By just looking at a certain area around that point, we can tell that the switches from increasing to decreasing, that's the highest point in that section of the graph. We can't say that over here because the arrow just keeps going. There's no way to pick a single highest point in that scenario. Similarly, right down here, as you may expect already, this is a local minimum because in this area of the graph, this is the single lowest point. It does continue lower over here, so it's not the absolute minimum, but it is a local minimum at least, just in that portion of the graph. And the way that we distinguish a local minimum is that it switches from decreasing to increasing. Okay. So our interpretation of local extrema depends on this understanding or knowing where the graph is increasing or decreasing and the transitions it makes over the course of its domain. Now, we may only have one absolute maximum and one absolute minimum, but it is possible, depending on what the graph looks like, that we may have more than one local maximum and more than one local minimum. Because these are just their one part of the graph. These are the highest or lowest values respectively. And there may be multiple parts of the graph where this happens, depending on the shape of the graph itself. Okay. So, let me give you another example. let me move to a new page, sorry. Nope, not there. There, sorry. And right there. So I've labeled 5 points in the graph, A, B, C, D, and E. And so the question is, which of these, if any, are absolute maximums? So is there an absolute maximum, first of all? So is there one point on this graph that is higher than all others? Now it looks like D might be, but that's just because we haven't labeled any points further up. And we could label a point here and call it F, for instance. But even F is not the highest point in the graph because it just keeps going beyond that. In this case, we would say there is no absolute maximum. What about an absolute minimum? Point A, yeah. A is an absolute minimum, right? A is the absolute minimum, yes. So that is the lowest point in the graph, vertically speaking. What about a local maximum? Again, local maximum occurs where the graph switches from increasing to decreasing. Visually, we would think of the local maximum as being at the top of a hill. Okay. So not point F. F actually does not fit any of these extreme values because it's a point on an increasing curve. So it doesn't really, hit an absolute value max or min, and neither a local value max or min. So if we think of the local maximum as a point that's on the top of a hill, which point or points seems to best coincide with that? Point D. Yes, point D. There is a second point that is a local maximum. B and D. Yes. Yeah, in each of these cases it's increasing, then it's decreasing, increasing, then decreasing, which makes points B and D both right. And both of them will be local maximums. And again, those are the top, that's like the top of a hill. So we go up, then we come back down. We go up, then we come back down. So that's right at the very top. That's our local maximum. Visually, that's how we're kind of discerning it. Well, in that case, what is the local minimum? Or minimums? Minima. However we pluralize it. C and E. Again, here it's decreasing, then increasing, decreasing, then increasing. And so that makes both point C and point E a local minimum because they're right there at the bottom of the hill. Okay. So we have another graph, same 4 questions. What is our absolute maximum in this case? We don't have any arrows, so we know the graph doesn't keep going. So this is the entirety of the graph right here. The other way we can think of the absolute maximum and absolute minimum is kind of the endpoints on the range. So if we look at the range of this graph, how low it goes and how high it goes, if it stops at a particular value, that's usually the maximum and a minimum right there, the absolute maximum and minimum right there. So the absolute maximum is C. This point is higher than all others. Okay, none of them go higher than this where this point is located. What about our absolute minimum in this case? As far as the absolute minimum goes, we won't have, it won't be, yeah, it'll be B for a minimum. Good. Yeah, A is kind of in between, so we can't really count it for an absolute. What about a local maximum? Again, local maximum, the only requirement we have is that the graph switches from increasing to decreasing. Is there a point where that occurs? C and A? Or just C? Well, for sure, C is a local maximum because it switches from increasing to decreasing. Now, the problem with A is that, okay, after A decreases, but to the left of A, is it ever increasing? Well, there's no graph to the left of A, so we don't know what happens there, and therefore we can't say it's increasing or decreasing. And so we know that it decreases after A, but because there's nothing to the left, we can't call it increasing or decreasing there. Okay? When we have an endpoint like that, like A and D are basically endpoints, endpoints ultimately will never be local extrema. They potentially could be absolute maximum or minimums, but never local. Yeah, and then there's a delay getting back to me. Sorry about that. I wish it was more instantaneous, but that's what we're dealing with. Okay, finally the local minimum. B. And that would be it. Yeah. The B right here, we're switching from decreasing to increasing. Yeah, and so what we notice in this particular graph is that point C is both an absolute maximum and a local maximum. So it is possible to be both of those. And point B is both a local minimum and an absolute minimum. And it really just depends on the graph what happens. There's no requirement that says we have to have any absolute maximum or minimum. So if we have arrows at both ends where the graph ultimately goes from negative infinity to infinity as a range, those never have an absolute max or min. Okay? The absolute minimum only occurs if there's really some highest value or lowest value in the graph, and if we have an arrow that says it keeps going to infinity both directions, then we're never going to have that maximum or minimum. That one point that's higher than all others or lower than all others. But local extrema, we can have multiple, as we saw in the previous example, and it may also be at the same location as the absolute extrema, as we see in this example. And so we're only looking at it based on the definition, not what we think should happen, but just what we're seeing. Okay. All right. So as you expect, the other problems in this section deal with identifying local maximums and minimums and absolute maximums and minimums. And we might have a few more problems with increasing and decreasing on our homework as we look at these other problems. As I left some of them out from the last assignment. Okay. So let's continue with section 3.4. Okay. Section 3.4 is on the library of functions and piecewise defined functions. Now, our library of functions is basically just a list of different functions, the names, including their names, and the general shape of the graph. It may vary from one to another, but they have the same general shape. So, we don't actually do a whole lot with our library of functions in Section 4. They're going to be more of a foundation for what we do in Section 5 on Wednesday. So our library of functions, what we'll do today is we'll kind of go through and just identify the different shapes and put a name to a graph, basically. And then we'll use this more as we move forward into section 3.5, but also into the sections after that. Okay. So we have a there's multiple linear functions we could use. If we have a horizontal line, for instance, this is called a constant linear function. And we might, whatever the y-intercept is here, call it b. We'll have f of x equals b, would be our function notation there. Now, we have a second linear function where it goes through the origin and is basically like a perfect diagonal, 45 degrees above the horizontal. This is called the identity function. It is also linear, but in this case, f of x is equal to x. And the idea on this type of function is that the y value is equal to the x value at every point. So we might have a point 2, 2. Over here it might be 4, 4. Negative 3, negative 3. Whatever the x value is, the y value is the same one. The y value is identical to the x value. And that's what this identity function represents. We also have what we might refer to as a general linear function. In this case, f of x equals mx plus b, whatever m and b happen to turn out to be. So all three of those are linear functions, and we do have names for each of those, but they're also all under that heading of linear function if we wanted to include it like that. The book does distinguish them a bit, though. That's why I wanted to go ahead and write them separately here. Each of these are part of our polynomials. We have a linear function because it's just m times x plus b. In this case, m is 0. In this case, b is 0. And m is 1. And this is a more general case right here. This is our quadratic function. Which forms a graph in the shape that we call a parabola. And our formula here is f of x equals ax squared plus bx plus c. Now, if we just have our basic parabola going up from the origin, this is f of x equals x squared. That's kind of our root function here. And then everything else is modified based on that. Okay. A graph like this is a cubic function. We don't have a name for it, but this is f of x equals x cubed. It's kind of like a parabola. Like if we look at the right hand side here, it kind of resembles the right hand side up here. And what is different, though, we see on the left hand side it curves down instead of up. So in a way, a cubic function is, we took a quadratic parabola and twisted it so that one side went down instead of up. And because of the higher exponent, it's been kind of squashed horizontally also. So it ends up looking a little bit taller in both directions and a little more vertical, I guess. Now, if we wanted to graph f of x equals x to the 4th, or x to the 6th, or x to the 8th, those would all look very similar to x squared graph. Okay? As long as we didn't have any additional terms added or subtracted, it's just x to an even exponent. They all have the same parabolic type shape. Although as the exponent increases, it gets more narrow and more tall as a result. Similar thing happens with x cubed. Like if we change this to x to the 5th, or x to the 7th, or x to the 9th, it would again have the same similar shape, but each time we stepped up and increased the exponent, it would shrink it horizontally and stretch it vertically. Alright, so those are our polynomial functions, or basic polynomial functions. We have our root functions, or radical functions, if you will. First of all, our square root graph looks like this. Sure thing, Amanda. Which one are you trying to look at? Did you want the linear ones? Okay. Mm-hmm. Our quadratics, and then our cubic. And now our square root function. Square root is basically like a parabola that now points to the right. Now, we can't have the bottom half of this parabola because if we had both the top and the bottom half, if we did a vertical line test, it would cross it twice and it wouldn't be a function. So with the square root function, we have to choose, do we want the top half or do we want the bottom half? And that's based on whether this is positive for the top half, or if this was a negative square root of x, we get the bottom half instead. But it does appear that we're missing half of that graph, because normally it would be a parabola facing to the right. But that's because in order to be a function, we can't have both halves. But it works out from a function perspective as well, because we can identify each half as either the positive half or the negative half. That's a question that we'll go into more detail with in section 5, as far as how those interact. Okay. So after the square root, we need a cube root function. Which looks like that. It actually looks a lot like the cube, or the cubic function, except now it's rotated to go left and right rather than up and down. Because our x cubed, remember, looks like this. So it's really the same picture, but it kind of rotated around and flipped. Okay. This is f of x equals the third root of x There's a few other ones we have that are considered special graphs, separate from those. They don't fit kind of our hierarchy of like polynomials versus root functions. We have the basic rational function, which looks like this. This is actually called our inverse function. Actually, no, not our inverse, our reciprocal function. That's probably the correct word. This is f of x equals 1 over x, but we call it the reciprocal function, but it actually is a rational function because it is 1 divided by x, so x is on the denominator, which makes it rational, even if the top is just a constant. Now, for the reason we call this the reciprocal function is whatever number we plug in it returns the reciprocal of that number. So if we plugged in x equals 3, it gives us 1 over 3, which is the reciprocal of 3. If we plug in x equals 1/2, it gives us 2. That would be the reciprocal of 1/2. The reciprocal is where we flip the fraction over. So if we have, x equals 3, which is 3 over 1, the reciprocal will be 1 over 3. Okay. Let's see. We also have the absolute value function, which is a V-shaped graph. F of x equals the absolute value of x. Now that's where we use the vertical bars to represent the absolute value. And the absolute value basically represents the positive, the number that relates to distance of the value from 0. So if we have x equals 3, 3 is a distance of 3 from 0. But if we have x equals -3, -3 is also a distance of 3 from 0. So f of 3 is 3 in this case, but f of -3 would be +3 in this case. Ultimately, the idea is that whatever number we plug in, it makes the number positive. So if we plug in a positive value, it stays the same. If we plug in a negative value, it makes it positive by default. Okay. So that's our what we call our library of functions. The only problem on this that we'll have in section 4 is it's pretty straightforward actually, and it's really just matching a shape with a description. Okay, and so I'll give you all of these problems from 11 through 18 on your homework, and you just have to match which shape goes with it. And that goes along with what we're talking about, is just being able to recognize what shape of graph goes with, what descriptor, what name do we have for that function, basically. Okay. Now, we will do more with the library of functions in section 3.5 on Wednesday, like I said, but at least for today, that's the extent that we cover it. The other topic we want to look at today is what's called piecewise defined functions. The easiest definition is that it is a function that is defined in 2 or more pieces. But then you might ask, what does a piece of a function mean? Well, let's look at an example. This is a function defined in 2 pieces. We'll say that we'll evaluate f of x as being 2 times x plus 1 if the value of x that we plug in is less than or equal to 1. If we plug in a value of x that is greater than 1, then we define f of x as x squared plus 1. So basically f of x has two different definitions here. One definition, if we plug in a value that's less than or equal to 1, and then a second definition, if we plug in a value that's greater than 1. Now, for our part, in this section, we're not going to graph these. We're just going to look at how to evaluate a piecewise function at a coordinate, or at a value. Not a coordinate, but at an x value. So for instance, in this case, if we wanted to find f of 3, would we use the first definition or the second? So we're plugging in a value of x equals 3. Is that less than or equal to 1, or is that greater than 1? So which of those two will we use to define what f of 3 is? Now 3 is greater than 1, so that means we will use this definition, x squared plus 1. Yeah, because the value of x that we're trying to plug in is bigger than 1, that tells us we want to use this piece of the function. If the value had been smaller or equal to 1, then we would use this other piece instead. So we use f of x equals x squared plus 1, then we plug in 3, and we get 3 squared plus 1, which is 10. Okay. Let's keep looking at these. F of x equals okay. Here we've defined a function in 3 parts. F of x is equal to 3 if x is less than or equal to negative 5. F of x is equal to x squared if x is between negative 5 and 1, including the 1. And it's equal to x plus 7 if x is simply greater than 1. So we have to pay attention to where it says greater than or less than or equal to. Specifically where it's equal to, that means, you know, when you want to make sure we get the right one there. So what if we wanted f of negative 2? So that means we're plugging in x equals negative 2. And we have to choose which of these 3 pieces of the domain is this negative 2 part of. Is it less than or equal to negative 5? Is it between negative 5 and 1? Or is it greater than 1? The second one, yeah. This negative 2 falls in between negative 5 less than x less than or equal to 1. So we use f of x equal x squared, since that's the definition that goes with that domain. And so f of negative 2, in this case, is negative 2 squared, which will give us a value of 4. Does that make sense so far? Let's try some others. What if we want to plug in x equals negative 7? Does that mean it's part of the first one, the second one, or the third one? First? Mm-hmm. Negative 7 is less than or equal to negative 5. So we use f of x equals 3. And then f of negative 7 in this case. Now, we notice there's no x in this equation. It's just a constant number. So f of negative 7 is just 3. Now, you don't have to write as much detail as I'm writing down here, but what I'm trying to include here is kind of our justification for using that particular piece of the function. We know that because the value of x we plug in is between these two numbers, we'll use this function here and then calculate it. Because this number, negative 7, is part of this domain, which is less than or equal to negative 5, we'll use this function and then plug in our value and evaluate. Okay. Part C, we want f of 4. So if we have a value of x equals 4, which of those three pieces does it fit in? Third one? Mm-hmm. Yeah, this is x is greater than 1. 4 is certainly part of that because 4 is bigger than 1. Okay. And because it's part of x is greater than 1, then we'll use f of x equals x plus 7. So f of 4 would be 4 plus 7, which gives us a value of 11. Okay. Is that all right? One last question. If you want to evaluate f of 1, in this case x is equal to 1, which one of these is x equals 1 part of? First, second, or third? second. And this one's, we have to be careful, because when we say x equals 1, x equals 1 is kind of a transition point for this domain, because that's where we switch from using 1 to the other. But, so this is x less than 1, this is x greater than 1, but only one of them is going to have the equal to part, and that equal to part is what we're looking for. Where is x equal to 1? When we look at this definition here, or the domain for this definition, it says x must be, between -5 and 1, but the less than or equal to right here means we also include the 1 itself as part of this domain. So we'll use x squared here. So we use f of x equals x squared, and f of 1 then would be 1 squared, or just 1. Okay. So I'll give you a couple of those that you can practice on the homework. But mainly it's just identifying which piece we have to plug the value into, and then plug the value into that piece of the function and evaluate it. And that's just like what we're doing here. Okay. All right. Now our homework is in 2 parts today, because of the 2 different pages that we worked on. Let me give you the second one first. On page 250, look at 19 through 26. As well as 27 and 29. And before that, on page 238, which you can't see. There you go. Let's see. There we'll look at 17 through 24, as well as 33, 35, '51 and 53. Okay. It looks like a lot, but these first problems in each section should go very fast, and then you might need a little bit more time for the others. Okay. I don't know if these will go. These are just reading the graph, and actually all of these problems in the first section, 3.3, are all about reading the graph and then finding results based on that. And then the second one, this is just matching problems to the shape of the graph to the name that we call that shape. And then 2 problems with piecewise defined functions and evaluating them at different values. So that'll be our homework today. So please look at those and be ready with any questions if you have on Wednesday. And then on Wednesday, like I said, we'll do 3.5, which will wrap up our discussion of Chapter 3. Yeah. Well, you all have a good rest of the day, and I will talk to you again Wednesday. See you later.